Hello, I'm Bakji Cecilia Nguyen. Today, I'll demonstrate how I built a machine learning model to predict power plant energy output. This presentation serves two purposes. First, as a technical case study showcasing the complete ML workflow, and second, as an educational walkthrough explaining key concepts and terminology in service of those who are new to machine learning. Throughout this project, I follow the CRISP-DM framework, the cross-industry standard process for data mining, which consists of 6 phases, as you see here. Starting with phase 1, business understanding. My objective is to predict electrical output based on environmental conditions. This is a supervised learning regression problem. Why? Because our target variable, power output, is continuous and numeric, not categorical. We have labeled historical data, making this supervised learning. Understanding data. I worked with structured tabular data stored in CSV format, making it ideal for traditional regression algorithms. As you see, each row represents a single observation, one moment in time at the power plant, and each column is a feature. Our 4 input features are all continuous numeric variable. These are our X variables, the predictors. I'll target the Y variable that we want to predict, which is electrical power output ranging from approximately 420 to 496. This structure allows us to apply a range of algorithms without needing additional feature extraction, unlike unstructured data such as images or text. Next in the process, data preparation, which includes exploring data to understand feature relationships so we can make an hypothesis before running the model training and validation. As you see on the right, I create a correlation heat map, which reveals crucial insight. Temperature shows a very strong negative correlation, negative 0.95 with power output. As a gut check, this makes physical sense. As ambient temperature increases, power plant efficiency decreases, thus resulting in lower output. In addition, you see multicollinearity as well between temperature and pressure. They are highly correlated at 0.84. What means by this is they tend to move together, which affects how models assign importance between them. The other 2 factors have minor effects, as you can see here. Okay, so these correlations set our expectation. Temperature should dominate our model prediction, which we will verify in our model training and analysis. Next, modeling. For the models, I compare 3. Linear regression, which is a parametric baseline, assuming relationship between X and Y as a linear relationship. Random forest regression and XGBoost are both non-parametric. In random forest, each tree is trained on a random subset of data and features, which is called bootstrapping, aggregating, or bagging. XGBoost uses a gradient boosted tree, but using boosting instead of bagging. Trees are trained sequentially, with each new tree correcting errors from the previous one. As for evaluation metrics, I ran 3. However, we have used 2 here as a primary evaluation metrics. The RMSE, root mean squared error, is the average prediction error. The lower, the better. And secondary evaluation metric, the IRAN is R2, which is coefficient of determination, which explains the variance by the model. We want higher is better with a max of 1. Total explainability. The selection strategy is to choose model with the lowest validation of RMSE and maintaining a high R2. Phase 5 evaluation of model performance. I split the data using the standard approach, 80% for training and 20% for test set to evaluate. Within the training set, I use validation to compare models. Here are the results of the validation set. Linear regression achieved RMSE of 4.5 and R-square of 0.93. That's the 93% of variance explained. This strong baseline confirms the fundamentally linear relationship in our data. Random Forest and XGBoost perform well with improvement, with XGBoost performing best, with RMSE at 3.02 megawatts and R-squared of 0.969, explaining 97% of variance. Just a reminder, with RMSE, the lower is the better. So to put this in context, it's about approximately 4% error, which is excellent production-ready accuracy. I also included the scatter plots visualizing the actual versus predicted values for the models on the top right-hand corner as well. Model interpretation, feature importance. Using XGBoost built-in feature importance, let's explain what drives the prediction. Ambient temperature dominates at over 90% importance. It's the overwhelming predictor and aligns perfectly with our correlation analysis done earlier. Air pressure contributes about 6%, which is a secondary influence. As a reminder, it's correlated with temperature, so some of its predictive power is already captured by the temperature feature. Relative humidity and exhaust vacuum each contribute minimally. So why does temperature dominate? Let's interpret in real-world context. Power plant efficiency decreases as ambient temperature rises. The Carnot efficiency principle tells us that higher temperature reduces the thermodynamic efficiency of the power cycle. Thus, our model has learned this real-world physical relationship and demonstrates proper model interpretation. We can clearly communicate not just how well the model works, but also why it makes the predictions the way it does. Conclusion and recommendations. There are 4 conclusions. First, the relationship is fundamentally linear, as we predicted and verify. Even simple linear regression achieved 93% accuracy. Second, temperature is the critical factor with over 90% feature importance. It's the primary control lever for power output optimization. So in real life, operators should focus monitoring and intervening on temperature management. Third, ensemble methods like Random Forest and XGBoost reduce prediction error by approximately 33% compared to the baseline. And finally, XGBoost is optimal, achieving the lowest RMSE while explaining 97% of the variance. My recommendation is to deploy XGBoost as the production model. And finally, phase 6, deployment. Now, as a gut check, before we deploy a model, let's revisit in a business context, why do we do this project? This model clearly delivers a business value, which is operational benefits. That includes predictive output forecasting, optimizing efficiency management, and early warning for performance drops. I also included some of the deployment plan and also monitoring strategy to track and detect model drift and periodic retraining and audits as needed. In conclusion, this project demonstrates understanding of the complete machine learning lifecycle from business understanding through evaluation and deployment and monitoring, the full CRISP-DM process.